Okay, so welcome back to the machine learning for 3D data. So last time we were discussing some kind of the new representations for the 3D shapes, which is basically having some kind of the implicit function. The function itself becomes some kind of representations for the 3D shapes. And we specifically discussed some kind of the ideas in terms of like making a neural net that becomes of the implicit representations for these 3D shapes. And we basically mainly discussed some kind of the two ideas in terms of like, what would be kind of the output values of the function. And the one idea was basically outputting the signed distance, and the other one was basically simply outputting the occupancy the information. And there are some kind of the several kind of the advantages having the neural representations in terms of that it's basically very compact representation. And while it can also record some kind of the fine details, as basically it's the also agnostic to the resolution of the kind of the output. So it doesn't need to specify the number of the points or the number of the voxels with some kind of the other the representations. So it can vary the output, the resolution, and also the topology-wise, it was very flexible, the representation. The only kind of downside for the implicit neural representation was that it is basically taking long time to produce like one single shape, because we need to basically query all the points in the 3D space in terms of the getting either the signed distance or the occupancy, the information. And in terms of like designing the neural networks, for that, we also discussed the idea of the siren and the free feature networks, which is basically either mapping the either the input or the output of each layer of the neural network into the sinusoidal the functions. In terms of that, we can better capture all the defining the details, the high frequency details. So by simply replacing the activation from the ReLU to the sine or the cosine of the function, we could get much precise the reconstruction the outputs like this. And this idea also could be applied to the images and also audios and many other the data modalities as well. And even with this kind of the new activation function, we could also consider basically reconstructing the input, the signal, either the images or the audios or the 3D, even only with the gradient information. So this was also quite interesting aspect. And we also could do the same thing by just mapping the input into the sinusoid of the functions. And by just controlling the frequency of either the sine and the cosine the functions, we could also control over the underfitting or the overfitting of the outputs, as we can see in this kind of example. So as we basically increase the frequency of the sine and the cosine function, we can better capture all the fine details, while there is kind of the risk that we can basically get some kind of the overfitting results like this. But if we also decrease the frequency of the sine and cosine function, we can get some kind of a smoother the outputs, which might basically also lose some kind of the details in the given the functions. So depending on the task and also the input the data that we have, we can control the frequency of the sine and cosine functions in terms of like controlling this kind of the underfitting and the overfitting. So these are some kind of the technical ideas in terms of like how we're gonna make some kind of the implicit the neural representations. And based on that, what we also discussed last time was basically how we can also do some kind of the 2D to 3D reconstruction. So this was kind of like simple the idea in terms of that we are having some kind of the encoder for the 2D images and having the decoder for the 3D, which is basically decoding some kind of the implicit function as the output. And we also discussed the idea in terms of like how we can make some kind of the some better the integration between the input image encoder and the 3D decoder in terms of like not taking the global features for the 3D the output degeneration, but just taking the per pixel the features to basically predict either the sign distance or the occupancy information for the corresponding the 3D point. So this was basically also the basic idea for the PyFlow architecture. And do you have any questions for the things that we discussed last time? So what we are going to discuss for today is also about basically how we are going to do some kind of the better reconstruction of the 3D from the images, especially for the not single image, but from the multi-view images. And the thing is that if you took the computer vision course, you might actually hear about that. Actually, there are some kind of the more kind of the traditional the techniques that can do some kind of the 3D construction using not using any kind of neural network. That's the kind of the idea which is called either the SLAM, simultaneous localization and the mapping, or the structural motion, which is basically the technique that we can do some kind of 3D construction from the multi-view images. So actually the underlying the idea, the basic idea is quite simple in terms of that. It's basically sort of like simulating kind of the way that the humans basically sense the depths with the two eyes. So with the kind of two eyes, we can basically kind of like feel some kind of the distance from the eyes to basically the object in the scene, right? And the basic idea that in terms of we can do the same thing with some kind of the calculation is that once we basically have some kind of information about some kind of the corresponding the points across the different views, what we can do is that actually we can backtrack some kind of the points in terms of the like where this point came from in this 3D space, in terms of like shooting the ray from the camera through this point in the in the three-dimensional space. So let me switch this into the razor point. So now we can see, right? Yeah. So we are basically backtracking this kind of the trace of the points over the 3D space in terms of like finding the 3D point which has been projected over this 2D point. And since we know the corresponding the point in the other view like this, we can basically also try to find some kind of intersection between these two rays, right? So this is kind of like example that we are having this point in this like the first image and having the corresponding the pixel in the other image, right? So based on this correspondence information, if we shoot the rays from these two cameras and finding the intersection the point, then basically we can backtrack some kind of the point, the 3D point, which has been basically projected into these 2 points. This is some kind of the very simple idea. Obviously, this is like involving lots of some kind of the steps in terms of like how we're gonna find some kind of the corresponding the pixels across the images, and how we can also get some kind of this kind of camera pose information, basically the information about like where the camera is basically placed in this 3D space, and what's the viewing direction for those kind of the cameras. So those information also should be obtained from the multi-view images. And based on that, basically we can do some kind of some 2D to 3D reconstruction based on that the correspondence information. So this is like actually a very old idea. I guess some of you might hear about this kind of the technique, which is called structure from the motion. And even like about like 16 years ago, we could see some kind of very amazing kind of results, which is actually reconstructing some kind of the entire building like this. So this is kind of the results that we are collecting some images. So let me switch the pointer. Okay. So let me replay this. So how we can switch it. Yeah, I don't know how I can replay this. But basically what we can see is that so these are some kind of results that we are collecting the images of the city of the Rome from the internet. So after collecting all the images, based on the kind of the techniques that I just mentioned, basically finding some kind of the corresponding the pixels and the shooting the rays into the 3D space, we can see some kind of results, like getting some kind of the reconstruction of the like building or even the entire the city like this. So you can see that those kind of the black, some kind of some of the cones here are representing some of the cameras of the images. And from those kind of images, which are basically taken from those kind of cameras, we are reconstructing the whole scenes like this. So this is kind of a really interesting technique in terms of that we can do some kind of the 2D to 3D construction without any kind of the learning. So this is really kind of some reconstructing the task that can be done without any kind of some supervised learning the process. And there is also the library, which is called the ColdMap, which you can just like download and see. You can just take the multiple the images from the objects or the scenes and see how much this kind of library can also reconstruct the 3D outputs. So this is kind of some very traditional techniques that we are going to see. So what we are going to discuss for today and also the next lecture is basically about some very basic techniques that are basically required to make this kind of the framework for the image to 3D construction. And after that, actually, we are also going to see some kind of the limitations of such kind of techniques. That you can see like one big limitation for such technique is that while we can see some kind of readily some kind of structure, the 3D, so we can see some kind of like how the buildings are basically arranged in the city with some kind of some rough the shapes for all the kind of the things here, right? But as you can see, the outputs are kind of some sparse the point cloud. So it's not really giving some kind of the clear the picture for the 3D from any kind of random view. So it's more about just like giving some kind of the sparse point cloud in terms of giving some structure information, but not some kind of some fine details, some kind of clean images that they get from any random views. So here the question is that how we can also utilize some kind of the power of the neural network in terms of that we can also get some kind of more defined details and so also the clean images from the random views. So that's kind of like what we are going to discuss with the neural rendering. And we're going to discuss that probably next Wednesday. And before that, to discuss some kind of the more details about the neural rendering, we will need to basically discuss some more the basic kind of things. So that's basically things that we are going to discuss for today and also the next lecture. So before getting into some details for those kind of things, what we are going to discuss is the camera model, which is basically some kind of the sort of the mathematical representations about the mapping between the 2D to 3D and 3D to 2D. And some of you who already have taken the computer graphics or the vision the courses might be quite familiar with these things. So I'd like to ask you, like, how many of you have taken the computer graphics or the computer vision courses before? You answer like yes or no? So yeah, many of you have already taken the computer graphics or the computer vision the courses. So for some of you who already have some background in the graphics or the vision, the things that we are going to discuss might be some kind of the very basic kind of things. It could be just like reviewing some kind of the background of the graphics and the vision. And the other the people who haven't taken the vision or the graphics courses, this will be some kind of some very basic things, some essential things that you need to know, not only to basically follow up basically the things that we are going to discuss in the later the lectures, but also to do the assignment as well. So for the assignment 2 and 3, you need to basically have some good understanding for the camera model to implement some kind of details there. And this also kind of basic idea would be very important for your the course project as well. So if you have any questions on this, let us know. So let's quickly go through into some kind of some basic things here. And as I mentioned here, we are not gonna get into any very deep kind of things for those things because we're going to just like cover those things in just like the one lecture. So we won't have time to discuss like every single detail for the camera model. So if you're more interested in the camera model, I recommend you to take some kind of the advanced the graphics or the vision the courses, which you can the best kind of place to discuss some more details. Okay, so what we are going to discuss for today is about some kind of the pinhole the camera model, which is the simplest the camera model, not assuming having any kind of some sophisticated lens in the camera, but just like assuming that everything is like projected into the image plane through a basically very tiny kind of hole in the camera box like this. So when you basically see some kind of this kind of the box, which is having some like very tiny hole here, and when you basically assume that all the kind of the rays are projected over this plane through this kind of the small the single the point here, then after the projection, the output that we are going to see is this kind of the upside down the images. This kind of the phenomenon is also called the camera obscura, which is getting some kind of some projected image through this single point. As you can see, the point at the top of the tree is basically mapped to some kind of point at the bottom. And also the point at the bottom of the tree is basically mapped to the top of the image plane like this. So this is kind of the very simple the model of the camera in terms like getting some kind of the 2D image of the 3D space by mapping everything in the 3D space through the single D point. So that's kind of the simplest model. So basically, we are going to discuss the simplest model, but while some the camera might have some more complicated kind of things. So we are not gonna get into those kind of things, but let's see. So for this simple model, what we can see is that we can easily calculate the coordinates of the point where the point is the projected. So let's think about like this simple kind of the setup that we are having some kind of even we are seeing some kind of the 2D slice of the YZ the axis, the YZ plane. So what we can see is that here we are defining the Z axis as kind of the direction where the point is basically the projected. So the ray is like coming from the 3D space, projected over the image plane along the Z axis, right? And you can see that the point at the origin is the pinhole, where basically everything is basically projected through this point. Yeah. And then we are having the image plane, which is located at when the z is 1, right? So we are having the image plane here, and this is the basically pinhole here, right? And all the points are basically projected through this point. So in this very simple setup, when you have the point which coordinates is the yz here, and what would be kind of the coordinate where this point is projected over the image plane. So basically what we can see is that obviously the z coordinates will be 1 because the plane is defined as it's kind of the place where the z is 1, right? The thing is that we just need to calculate this like y prime, right? What's the y prime here? Very easy, right? So the ratio between the y and z should be the same with the ratio between the y prime and the 1, right? Then we can say that actually the y prime should be basically simply y over z, right? Very simple. But the thing is that, if we just like project all the things into the image plane like this, as I mentioned at the beginning, what we are going to get is that we are going to get this kind of the upside down image, right? So what we are going to do is that after projecting over the plane on the z equals 1 plane, and then we're going to flip the image, basically flipping the sign of the y and the x-axis, right? Then actually what we can see is that actually projecting over the z equals the 1 plane here, and then flipping the images is actually equivalent to projecting onto the g becomes like -1 the plane. So as I said, I mean, when we basically project the points over the z is the plane here, and the flipping the image is the same as basically not projecting this plane, but actually projecting over this plane. So actually what we are going to see is that, so this is not basically exactly the things that we are going to do with the pinhole the camera, but mathematically, this is just like the equivalent things. The projecting over this plane is the same as basically projecting over this plane and then flipping the image. So what we are going to see is that we are going to assume that the projecting the process of the pinhole camera is actually projecting over this plane. Okay? So basically, so if we project the points here into this image plane, where the g is basically the -1, then what's the y, the double prime here? Yeah, obviously like minus like y over z, right? So that's basically what we are getting. So what you can see is that, so this is kind of the case that we are only seeing the 2D the slice with the YZ plane. But if we only also see this the same thing in the 3D space, what we can see is that actually the projection of the pinhole, the camera is basically the same as basically mapping all the X, Y, Z, the coordinates into this new point, which is having the coordinates of the minus X over Z, minus Y over Z, and the -1. So we basically are basically having a function mapping all the X, Y, Z coordinates into these kind of new coordinates. Clear? very simple. But here the thing is that how can you also represent this function into the matrix form? So we are going to see how we can basically represent all the things into the matrix form in a way that we can do the calculation much easier. And we can also represent all the things in like the more the compact way. So for that, basically, we are going to discuss the homogeneous coordinate system. So what we talk about when we talk about the homogeneous coordinate system, it's basically nothing but given any kind of the, for example, like 3D coordinates or for the 2D coordinates, whatever kind of the dimension of the coordinates, we are basically introducing a additional coordinate here, while basically having this kind of condition. So basically, you can see that while we are having the additional dimension here, we are having some kind of the, making some kind of spatial relationship across all the coordinates in terms of that, when you basically divide or multiply any kind of scalar into the vector, that becomes another kind of the identical coordinates. So while we basically have some kind of different coordinates for those kind of two vectors, we assume that these two are basically representing the same point. The point which basically have these coordinates like x over the w, y over the w, and z over w. So this is kind of thing. So we are just going to have some another dimension while basically having this kind of the some equivalence, some kind of the relationship across the coordinates. So basically, if we visualize basically what we are doing with the homogeneous coordinates, let's basically see some kind of a visualization for the 2D plane case. So in this like the 2D space, what we can see is that while we only have some kind of the x and the y coordinates, now we are introducing the new coordinate, which is w here, right? And then basically what we can see is that if we had like any point here, basically like multiplying any scalar to this point is basically identical, basically having some kind of the different coordinates for the same point. Which means that when you basically draw a line from this point, from the origin, like basically a line joining the origin and this point here, all the points along this line, except for the origin here, are basically representing the same point. So that's basically the idea. It's kind of like augmenting the space, the coordinate the system with the additional dimension, while having this kind of some sort of the equivalence relationship. So in the homogeneous coordinates, is there no constraint of x, y such as the union norm? No constraint. Yeah. So we don't have any constraint in terms of the norm of the vector. We just like have some kind of the relationship in terms of that, those kind of the coordinates become represent the same point. So that's the only thing. So which means that for the same the 2D point or the 3D point, there can be multiple ways to represent the same point. You can either divide or basically multiply any kind of scalar to the vector. That is not basically changing the meaning of the coordinates. It is clear? So this is kind of some kind of visualization in terms of that in the 2D case, like if we have some additional dimension here, like any kind of the lines passing through the origin here are basically representing the same point in the 2D space, except for the point at the origin here. Yeah. So these are some kind of the ideas about like having the additional dimension in the homogeneous coordinates. So based on that, basically the reason that why we are talking about the homogeneous coordinate is that we want to have some kind of the matrix form to represent this kind of the mapping, the projection of the pinhole, the camera. So what actually we can see is that when you have the x, y, z coordinates with the additional dimension of the one here, is this point is basically equivalent with like having these coordinates, like multiplying some kind of the scalar here, right? So based on that, basically what we can say is that so the mapping, the projection that we have seen in the pinhole camera model was basically mapping the x, y, z coordinates into these coordinates, right? And the identical, some other kind of the coordinates representing the same point is basically this. So when you also multiply minus g for all the coordinates here, it also represents the same point, right? So the projected point now also can be represented as the xyz minus z. So in the homogeneous coordinate system, now we can say that the projection can be seen as basically mapping the xyz1, this four-dimensional vector, into the xyz minus z. So that's kind of thing. So when you see this kind of the some augmentation into the four-dimensional vectors, now it becomes much easier to represent this into the matrix form. So based on this kind of the relationship, the mapping with the homogeneous coordinates, can you now represent this mapping and with the 4x4 matrix? I mean, yeah, please post your answer for the 4x4 matrix. So again, my question is not about like whether we can do that or not, but just like, please put your answer for the 4x4 matrix. So basically what we can see here is that when you have this kind of like dividing by z here, it was not possible to basically presenting this into the matrix form. But after using the homogeneous coordinates, now we can see that there is no basically dividing by zero here. I mean, we can basically just like multiply like minus z for all the coordinates, and we are getting this, right? And after basically having this kind of conversion, now we can see that the mapping from these the 4D coordinates, the homogeneous coordinates, into these 4D coordinates becomes some kind of linear mapping. Then now we can easily describe this into the matrix form. And actually, there can be also multiple ways to have that the 4x4 matrix, but this will be basically the case, right? So when you have the 1, 1, 1, and the minus 1, then we're going to see the results that we are mapping the xyz1 into the xyz and the minus z. And by dividing all those like 4D coordinates by the minus z, we can see some kind of final the projection, the coordinates, right? So you can see that the homogeneous coordinates are quite useful kind of the ideas in terms of representing this kind of the projective, the transformation into the matrix form. So that's kind of the basic idea in terms of like how we're gonna represent all these kind of camera models using the matrices. Clear? Any questions? So speaking to the homogeneous coordinates and also the projective the geometry, the projective space, also the interesting that we can do with the especially the homogeneous coordinates is that so let's see here what we can get. So this is kind of also the case that we are basically moving towards some specific direction over the 2D plane. So we are basically multiplying some w here to the x and the y here. That means that starting from the origin over this kind of the 2D plane, we are moving towards some specific direction. We are going into this direction like this. And then what we can see is that actually the identical the coordinates for the same point is the x, y, and the 1 over the w. So basically what we can see is that when you go over along this direction, like let's say like we are here, right? So on this point, actually if we also draw the line from the origin to this point, as I said, all the points along this line except for the origin here, are basically all the coordinates representing the same point, basically identical some kind of coordinates, right? So this point here is the same point represented with this point. So actually, so what we can see is that as we go further along this direction, from here to there, what we can see is that the corresponding point having fixing the x and the y here becomes like going down, down and the down, right? So when you here is basically having the x, y, and 1, as we go further into the wx and wy and the 1, we are going down to the x, y, and the 1 over the w. And as we go further and further and further, we can see that actually the corresponding point along this line is going down to the xy plane. Make sense? Clear? So what we can see is that if we go to the point at infinity, so that's the case that we are basically having the infinite number for the x and the y coordinates, right? But actually we can represent the point at infinity with the finite the numbers, because the corresponding point or the point at infinity will be also have the some kind of the identical some coordinates, which becomes like x, y, 0. Right? So from what we can see, like this relationship is that as we increase w and just like basically increasing the w to the infinity, the corresponding the coordinates that we're gonna get is will be x, y, 0. So which means that now we can represent the point at infinity with the finite numbers. So in the projective space, the interesting thing is that we can also define some kind of the finite coordinates for the points at infinity. So now we can basically define the point at infinity. So that's kind of the interesting kind of things, and also interesting the difference with the Euclidean the space. Make sense? Then how many points at infinity do we have for each of the direction? So also the thing is that when you go to the one specific direction, you're gonna see like one point at infinity. But if you go back to the other direction, the opposite direction, the thing is that you're gonna actually meet the same point at infinity, right? Because when you have this kind of a relationship, as you basically increase the w to the plus infinity or decrease w to the minus infinity, at the end what you're gonna get is basically the same kind of the coordinates, which is the x, y, 0. So which means that, interestingly, the two extremes meet at the same point. Whether you go to the one direction or you go to the other the opposite direction, if you go to the infinity, we are basically going to the same point, which is having the coordinates of the x, y, 0. So what we can say is that for every direction, there is only one single point, one single the point at infinity. So this is kind of some interesting, some kind of structure of the projective geometry. Make sense? And then here the question is that what is this this like the coordinate 0, 0, 0 representing in this case? So the thing is that with the homogeneous coordinate system, 0, 0, 0 is not representing origin. The origin should be 0, 0, 1 or 0, 0 something that is like non-zero value. But if you have like 0, 0, 0, which defines nothing. So this is basically invalid coordinates. So we should not use the 0, 0, 0. It's like representing nothing. So that's kind of things that you should not be confused. So if we want to represent the origin, there should be 0, 0, 1 or 0, 0 something non-zero the value. But if you have like 0, 0, 0, there is no way that we can define point at infinity without having any kind of direction. So the point at infinity is basically defined with any kind of the direction. But if you basically have the 0, 0, which is not defining the direction, then this becomes something representing nothing. So 0, 0 is basically some invalid, some kind of coordinates in the projective geometry, with also with the homogeneous coordinates. Clear? So there are some kind of the interesting, some kind of the characteristics of the projective space. And to see some kind of more interesting kind of things, let's first see how we also represent the lines in the space. So we can basically, in the two-dimensional space, we can consider this kind of the line equation, right? So ax by plus c is like representing a line, right? So we're gonna basically take these like three numbers as kind of the parameters for the line. So now let's say this ABC is representing a single line. And so let's do this, like the basic things first. So given this kind of the ABC, the parameters for the line, how can we check whether a point is on the line or not? I mean, so this is kind of very easy, right? So we can just like take the dot product between these two to check whether the dot product is zero or not, right? So by definition of the line equation here, if the point is on the line, then the dot product of like these two, the two vectors, the three-dimensional the vectors, should be zero, right? This is just like the by definition. And based on this, the question is that now let's think about like finding a line which is basically passing through the 2 points. Then how can you find such kind of a line? We just know that the point, if the point is on the line, then the dot product between these two should be zero, right? So based on the information, can you also find a line which is basically passing through the 2 points? So this is basically something that we are finding a three-dimensional vector, which dot product with this x and the x prime, both of them become zero, right? What is such kind of the vector? Three-dimensional vector, which dot product with these two, both of them becomes zero. So the answer for that is obviously the cross product. If we take the cross product like these two, that basically outputs the three-dimensional vector, which the dot product with each of them becomes zero, right? So based on this kind of representation, we can easily find a line which is basically joining the given the 2 points. And the interesting thing of like this kind of representation is that we can do some kind of similar things like this. So now let's think about that we are having two lines, having those kind of like the two different parameters. And how can you find the intersection point of those 2 points? Actually, it's the same thing. So we are also finding a three-dimensional vector, which is dot product with these two becomes zero, right? And we can also find the intersection point by taking the cross product of these two. So which means that the line joining the 2 points and the point like where basically the two lines are intersecting, both of them can be computed using the cross product. So this is something which is called the point and the line duality in terms of that we can find this kind of two things by just using the same cross product. So this is some kind of the basic things about with our the line representations. And also in terms of like the calculating the cross product here, also the way that we can also represent this with into the matrix form is to use the skew symmetric matrix. So this is basically nothing but what we can see is that when we compute the cross product of like these two, we can do the same calculation by defining this kind of the matrix and taking the matrix vector, the multiplication. So this is nothing but, we are basically defining this kind of the matrix that is basically skew symmetric, which means that this is kind of the symmetry, except for that we are having the different sign here. You can see the W and the W, minus Y and the Y, and the X and the minus X. So given the coordinates of the first the vector here, instead of like calculating the cross product, now we can define this kind of the matrix here and take the matrix and the vector the multiplication. Then this gives the identical the outputs. Right? But this is nothing but the way that we and how we calculate some kind of the cross product with some kind of the two vectors, right? Clear? Anything that is not clear to you? So based on this kind of the basics here, the one thing that I'd like to ask is that, so now in the projective space, let's consider like finding some intersection of the point. So now we have the two lines. One is the 2x minus 3y equals 5, and the other one is the 4x minus 6y equals 2. So given these kind of two lines, what's the intersection point? We have discussed like all the ideas in terms of how we can calculate the intersection point with the two lines, right? So let me give you like 2 or 3 minutes to think about this. So actually what we can see is that, so we have seen like how to calculate the intersection, the point with the two lines here, right? So it's the matter of like calculating the cross product of the line parameters, right? So let's just like calculate the cross product of the two line parameters. Then what we can see is that actually we can get the point, the intersecting point as the point at infinity. And what we can see with some kind of the visualization of the two lines is that obviously like these two are basically parallel lines. And when we basically go to the infinity of like along these two directions, actually we can see that actually these two lines also meet at the same one point at the infinity. So basically having the same slope for those kind of two lines. And after like going into the to the infinity, we can see that actually these lines meet at the same point, which is the point at infinity, right? So this is kind of the interesting in terms of that when we extend the Euclidean space into the projective space, where basically we are augmenting the points at infinity, we can see that actually all the lines, even the two parallel lines, meet at the one unique point. So whether the lines are parallel or not, we can see some kind of results that all the distinct lines are basically intersecting at like one point, and that point can be pointed infinity. So we can basically have some kind of a very general rule for the projective space in terms of that all two distinct lines are basically intersecting at the one unique point. So that's kind of the interesting some kind of characteristics of the projective space, which is basically happening based on our definition of the points at infinity. Clear? So whatever basically the lines you have with some kind of a different offset here, if the slope of the line is basically the same, then we're gonna see some kind of results that these two lines basically meet at the one single point. By calculation here, right? I mean, and also by definitions of all the things, right? So this is like the one interesting the characteristics of the projective space. Then also the question might be is that, so we have seen that the two parallel lines meet at the point at infinity. So now what if we have the two distinct points at infinity? What would be the line that are basically connecting these two? Can you also calculate the line parameters, like joining these kind of 2 points at infinity? So as we have done in the previous slide, we can also do the same thing in terms of calculating the cross product. And since we assume that these 2 points are distinct points at infinity, which means that these two are not the same, then we're gonna get these kind of line parameters, which is basically the same, basically dividing by this term. So now we can represent the line joining these 2 points as the 0, 0, 1. So which means that now we can also define the line joining 2 points at infinity. And the question is that would this line joining these 2 points will also pass through the other points at infinity? The answer is yes. So by just connecting, there is basically one straight line which is connecting all the points at infinity in the projective space. So that's kind of some very interesting, some kind of structure of the project space, which is defined by extending the Euclidean space with the definitions of the points at infinity. So based on this, also what we can see is that in the projective geometry, all the two distinct lines are basically intersecting at a one unique point. And also every two distinct points are basically having one unique line joining these 2 points. For any two lines, there is like one intersection point. For any two distinct points, we also have the line joining these two. So we can have this kind of very general rules for the projective space. So that's also kind of the difference with the Euclidean space. It is clear? So can you basically visualize the project space in your mind? So how it looks like in some kind of visualization. So we can consider, we can imagine some kind of some visualization for the project space in different ways. So basically, this would be the case that, especially for some kind of the 2D kind of case, in the simple kind of the 2D case, that's kind of the case that we are expanding the 2D plane like this, while at the end, at the point, at the kind of the, if you go to the infinity here, there is kind of the like one line which is connecting all the points at infinity, right? So if you go into the direction of the D here, there will be like one point here, which is identical point that you can see when you go to the opposite direction, right? So these 2 points becomes the basically the same point. And then there is like one line which is connecting all the points at infinity. So that's kind of some sort of the geometry of the projective space, right? And probably some kind of the easier way to think about this kind of the visualization of the projective space might be through the mapping to the plane over the sphere. So actually what we can say is that for all the points over the 2D, the projected the plane, we can basically define a 1-to-2 mapping from the point over the projected plane to the points over the sphere in the three-dimensional space. So actually what we can do is that, so this is kind of the projected plane where we're gonna also have the points at infinity and the line at infinity, and the top of the sphere like this. And for any point over this plane, if you draw a line passing through the origin of the sphere, there will be 2 points intersecting with that line, right? And you can see that for any point, even for the point at infinity, if you go to there, then the point at infinity will also map to the point here, right? Over the gray circle. So this basically means that for any point over the projected plane, we can define the 1-to-2 mapping. So that's kind of like showing some kind of interesting some geometry of the projected plane in terms of that actually the whole space can be mapped to the 2 points. Every single point is mapped to the 2 points over the sphere. It is clear? Then how is a line is mapped to the sphere. If you also have a line over the projected plane, that will be also mapped to the great circle over the sphere like this. So that's kind of the interesting things in terms of that. While we started from the 2D Euclidean plane, if we extend that with the points at the infinity and also the line at infinity, now we can see some kind of the mapping from the projected plane or over the sphere through the 1-to-2 points the mapping. So yeah, this is kind of the interesting some structure of the projected plane. Any questions on this? So this was kind of the very brief introduction about the homogeneous coordinate system and also the projective space. And based on that, actually, we can basically define the camera model. So when you come back to the camera model, basically, also what we can do is that, so we have seen some kind of example that where we are putting the camera, the image plane over when the Z is 1, right? And then flipping the image. And it was identical to putting the image plane at the where the point that when the z becomes like -1. But obviously, we can control the distance from the origin to the image plane. So we can set the distance from the origin to the camera plane, the image plane, not as the one, but any arbitrary number. And we're gonna call this the distance from the point to the image plane as the focal length. So if we put the image plane with the distance of the f here, and then flipping the image, would be also identical to putting the image plane with when the g becomes like -f, right? So we can set the focal length, which is basically becomes the distance from the origin to the image plane here. And then we have seen like how we can define the 4x4 matrix, defining the mapping from the projection from the 3D to the 2D, right? When the focal length is 1. But if the focal length is not 1, but f, then how would the 4x4 matrix being changed? So yeah, you can calculate this yourself and see that, when the image plane is located, when the z is basically -f, then it becomes like now the y prime, the mapped, the point, the y coordinates of the mapped point becomes like minus y over z times the f here. Then we basically are having this kind of mapping, right? Then now we can represent the projective the mapping, the matrix for the projective transformation as this kind of the matrix, like having f, 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 and the -1 here. Try yourself and see how we can get this kind of the matrix, right? So this is the case that when you set the focal length, which is the distance from the origin to the image plane. And the other way around that we can also set this kind of some camera parameter is not to set the distance from the origin to the plane, but actually, setting this kind of the field of view, which is defining this kind of angle. So we can consider basically having some kind of the fixed size of the image plane like this, having some kind of a certain the kind of the range from the -1 to the +1, while basically setting this kind of the view, the angle of the view, how basically wide this angle in terms like projecting all the things. Then you can see is that when you actually define the range of the image plane, for example, like from the -1 to the +1, and also basically setting some kind of the angle here. Based on that, actually, we can calculate the focal length and basically do some kind of all the calculation for the projection of the matrix, right? So let me skip this, but you can try this yourself and see what you get. Basically, given this kind of angle for this, the field of view, and from the range to the -1 to the +1, and actually what we can get is that from this information, we can calculate the focal length becomes of the inverse of the tangent, the half of the angle here, and just putting this into the focal length making some kind of the projection of the matrix like this, right? And also the thing is that when you define the field of view, actually we can set different field of view for each of the axes. For the focal length, it doesn't make sense that we set the different the focal length here. But depending on the range of each of the axes, actually we can set the different field of view, which is also changing some kind of size of the image along each of the axes. Right? So this is also the kind of the things. And also what we can do more is that we can do some more complicated kind of things. So this is kind of the example that we are now setting the focal length instead of the field of view. And what we do is that we are doing some kind of the shifting of the image plane in terms of that the center of the image plane is not along the z-axis, but above the z-axis, for example, here, right? While basically having some kind of the range which is not symmetric from the L to R to the B to T. And after projecting all the things into the image plane, we're gonna also normalize the image space in terms of that the L to R, this range is mapped to the -1 to the +1, and also the bottom to the top here is also mapped to the -1 to the +1. So we are basically not only doing the projection, but also normalization of the image space. Then also, can we represent like both this kind of combination of the projection and the normalization with like one single the 4x4 matrix? So I'm going to skip some details here, but I'd like to strongly recommend you to try this yourself and see what you get. But this is basically nothing but some kind of the calculation in terms of that we first basically map the each of the point over the image plane and applying some kind of the normalization to basically do this kind of the some mapping, right? From the range from the L to R is mapped to the -1 to the +1, and to the same thing for the x-axis and the y-axis. And based on that, now the mapping becomes like mapping this x, y, z, the coordinates into this kind of the complicated coordinates. And now we can see that this kind of the combination of the projection and also the normalization also can be represented with this kind of 4x4 matrix. So you can see that we are basically having some kind of scaling term here and some kind of translation term here with the f and the -1 here, right? So this is kind of the typical form that we can see for this kind of the projection matrix. So check out some more details about how we can exactly get this kind of the matrix. So let me go quickly for the rest of the slides. So these are some kind of the background that you can actually learn from the computer graphics course, and you can learn the same thing in the computer vision course as well. But the terminology that we are using in the computer vision might be slightly different. So what we typically see for the computer vision literature is that in the graphics literature, typically the z-axis is defined in this way, the way that the points are projected. But in the computer vision the literature, typically the z-axis is flipped. So the z-axis is defined as kind of the viewing direction from the 2D to 3D. So you can see that the rendering is basically, the graphics is like all about the rendering. So it's all about the mapping from the 3D to 2D. So the z-axis is defined from the 3D to 2D direction, while the vision is more about the 2D to 3D. So the z-axis is like flipped from the image plane to the 3D space. So in this kind of the flipped z-axis, like setting the focal length to be f, basically the meaning that we are placing the image plane at the when the z equals to f here, right? So it's nothing but it's like flipping the z-axis in this way. So without this kind of like the shifting of the image plane, in this case, the projection matrix will be defined into this way, f1, and we can say that this like 3D coordinates is mapped to the another the 3D coordinates. But typically for this kind of the mapping, we don't need the z information anymore. So after this mapping, actually this G represents some kind of still the depth information, which might be useful for many applications. But if we don't care about the depth, if we only care about the image, then we can basically drop this part. So in the computer vision literature, we typically also drop this like third row, which is representing the depth information. We only get basically the X and the Y information here. And we can also see that typically the last column is also just like the zero vector, like 0, 0, 0. So what we can do is that for like to make some kind of the more like the simpler the representation, we can consider basically dropping the last column here. So dropping this last column basically means that we are not using the homogeneous coordinates for the input the 3D coordinates. So the input 3D coordinates are basically non-homogeneous coordinates, not having the actual dimension, while still having the homogeneous coordinates for the output, the 2D here. So to get basically the final output here, we will basically need to divide this fx and the fy by z here. So this is kind of the way that now we can represent this kind of projection, not with the 4x4 matrix, but with the 3x3 matrix. Ignoring basically the z axis, the z coordinates for the projection, and also not using the homogeneous coordinates for the input, but only for the output here. Okay, so the projection the matrix now can be represented, is represented with the 3x3 matrix. And typically this 3x3 matrix is also called the camera intrinsic matrix. So basically this means that this like the matrix is basically encoding the camera the parameters in terms of how we're gonna project the things. So it's not the related like where we place the camera. It's more about some kind of the camera, some kind of the inherent, some kind of the information defined based on basically how we exactly make the camera, right? Some focal length or some kind of the shift of kind of the image plane kind of things. So as we also have seen in the previous slide, if we have some kind of the shift of the image plane, we're gonna also have some kind of terms here. So typically the camera, the intrinsic matrix is defined with some kind of the focal length here, and also kind of some shifting information of the image plane, while some of those kind of the zero values can be also the non-zero value. So if we have some kind of the non-zero values here, that is also representing some kind of the distortion or some kind of some shearing in the projection, the process. But in the simplest model, we are going to have some kind of some focal length information here, and also the camera, the image plane, the center information here. And this 3x3 matrix becomes the camera intrinsic matrix, and also sometimes it's also called the camera the calibration matrix. Okay. Any questions on this? So this was like all about basically how we exactly represent some kind of some projection the process of the camera with some kind of the matrix form, right? So after doing all this kind of some kind of calculation, we can say that this kind of the projection can be represented with either the 4x4 matrix or some kind of more the compact form into the 3x3 matrix. But this only basically describes basically how we're gonna project all the 3D things into the image plane. But when you also talk about some kind of the multi-view images, so this will be also the case that we will basically define some kind of the local coordinate system in the 3D space with basically different kind of the camera pose, right? So depending on where we basically put the camera, and also depending on the view direction of the camera, we are defining some kind of the local coordinate system in the 3D space. So that is called the camera coordinates. While we're gonna also define some kind of the absolute coordinate system, which is also called the world coordinates. So basically, we are typically defining the 3 coordinate system. One is the world coordinate system, which is some kind of the absolute coordinate system for the entire 3D things. And depending on where we put the camera and also the view direction kind of things, we're gonna also define some kind of a local coordinate system, which is the camera coordinate system. And all the kind of 3D things will be projected over the 2D plane, right? Then we are also having the 2D image coordinate system. So we basically have this kind of the 3 coordinate system. And basically what we have seen is that we have seen some kind of mapping from the camera coordinate system to the image coordinate system. But before that, actually, we can consider the mapping from the world coordinate system to the camera coordinate system. And this conversion from the world coordinates to the camera coordinates is typically called the matrix representing this is typically called the camera extrinsic matrix. So it's not about some kind of the camera, some kind of the some inherent some kind of the parameters there. It basically based on where we put the camera, right? Where we place the camera and how we set the view direction. And this kind of conversion from the world coordinate to the camera coordinates is represented as the rigid-body transformation, which means that it's basically involving some rotation or the translation. So, which means that now we can also represent this kind of conversion with the 3x4 matrix. The first part becomes the rotation, and the second part becomes the translation. So this is about the mapping, the conversion from the world coordinates to the camera coordinates. And once we basically convert everything into the camera coordinates, we're gonna also do the projection into the image coordinates. So that's the camera intrinsic matrix, which now can be represented with the 3x3 matrix, okay? With some kind of focal length with the image to the center information. So we can see that when we actually talk about the camera model, actually we are setting some kind of the two kind of the matrices. Like one is about the mapping from the world coordinates to the camera coordinates, and the other one is about the camera coordinates to the image coordinates. So the first one is for the 3D to 3D, and the second one is for the 3D to 2D. So only basically the camera model can be defined as kind of a combination of like these two. So we are having like one 3x4 matrix for the extrinsics and the 3x3 matrix for the intrinsic. And when you talk about the camera matrix, actually we basically mean by this kind of the combination of like these two. So when you multiply these two, this 3x4 matrix like which become the combination of like these two becomes our the camera D matrix. And for this kind of the representation, we basically mean by that we are having some kind of the non-homogeneous coordinates for the 3D input here, and having the homogeneous coordinates for the output, the 2D here. Makes sense? So this is the basic idea for the camera model, that we are having the two types of the matrices. Like one is the extrinsic D matrix, representing the rotation and the translation, and the other one is basically camera the intrinsic matrix, which is about the projection. Clear? Questions? So basically, when you talk about some kind of the 3D to 2D mapping or the 2D to 3D mapping, this kind of the mapping is represented with this kind of the 3x4 matrix. And also basically obtaining this kind of the matrix for the mapping is the process that we call as the camera calibration. So here the question is, how is the origin of the world coordinates defined? So it's up to us. We can define the world coordinate system as we want. So for example, like for the cases that we are reconstructing 3D from the multi-view images, which means that we are having the multiple cameras in the space, right? So very typical way that we don't need to, but the typical way that we can define the world coordinate system is to set the camera coordinate system of the first camera as the world coordinate system. So we define the world coordinate system as we want. And based on that, the absolute coordinate system, now we are defining some kind of local coordinate system based on the center of the camera and also some kind of view directions. So that becomes like involving some rotation and the translation. And once you basically see all these 3D things from that local coordinate system, we can apply some kind of the projection, which is defined with the intrinsic matrix here. Is it clear? So for the second and the third assignment, we will basically need to see basically how to deal with this kind of some extrinsic matrix or the intrinsic matrix and how to calculate those kind of things. So there might be some kind of parts that you need to work on. So one last thing, I'm not sure whether I'm gonna have time for that, would be basically about like, so how can we compute this kind of the 3x4 matrix, given some kind of the information about the 3D to 2D mapping? So for example, let's assume that we somehow have some kind of information about the point correspondence. For example, like given this kind of the scene, we define some kind of the coordinate system in this 3D, and we know the coordinates for those kind of some key point here, and we also can see some kind of the 2D coordinates in the image space for those kind of same the key point. So let's say we have some kind of the information about the correspondence for the 3D to 2D. And based on that, how can we compute the camera matrix, which is describing this kind of the mapping? So that's the process. It's called the camera calibration and also called the camera resectioning. So this is kind of the not simple kind of task as you kind of expected, but the thing is that we are basically having the non-homogeneous coordinates for the 3D points, but also using the homogeneous coordinates for the 2D coordinates, right? Which means that when you basically find some kind of the camera matrix P here, actually the P multiplied by the 3D coordinates may not be the same with the 2D coordinates, but we did some kind of scaled the version of the same vector, because this vector is the homogeneous coordinates. This is clear. So when you basically find any kind of the camera matrix here, when you basically map the 3D coordinates into the homogeneous coordinates of the 2D point here, the output of this kind of like multiplying the matrix here can be some kind of the same vector, but with kind of different scale. So basically, we don't know about the scale information, We just know that actually the multiplication like these two will be the vector, which is kind of some scaled version of like this vector. So these two are not exactly the same, but there might be some kind of scaling term that we don't know what's kind of exactly scale for that. So what we are going to do is that instead of like just like making these two be the same, we're just gonna say that actually these two should be the vector with the same direction, but probably with some kind of different kind of the magnitude. So which means that these two should be basically be kind of the vectors which are the parallel in the kind of 3D space. So which means that when you take the cross product like these two, the cross product should be 0, right? Does this make sense? So we basically use this information to calculate the P here. So what we can do is that, let's say now the P is like having the 3 rows. So P was the 3x4 matrix, right? So now we are seeing that P1, P2, P3, these are representing each of the row here. And we want to compute the cross product here. And we have seen that how we can compute the cross product with this Q-symmetric matrix defined like this one, right? So now we want to compute this. You can check the details later, but actually computing this is identical to now computing this. So the change that what we are seeing here is that now we are representing the 3x4 matrix P as some kind of some vectorized form. So now this is not the 3x4 matrix anymore, but actually concatenating each of the row in terms of that we are now having the 3 by it should be actually the 3 by the 12 kind of dimension, right? So it should be 12 here. So we are basically having some kind of vectorized form of the P matrix here. So it becomes actually we are solving this kind of the homogeneous linear system in terms of that we are having some kind of vectorized the form of the matrix and having the 3 equations here. But the thing is that actually only 2 of them are linearly independent. So which means that we can only take the 2 equations, these 2 basically homogeneous linear system for the vectorized form of the matrix here. So what you can see is that actually, actually it should be 9. Actually, it's the 3x3 matrix. Yeah. So actually, what we can see is that we have for every kind of the 2 pairs of the points, we are having the 2 equations. So as we have some basically n number of the point pairs, we can accumulate all the kind of the homogeneous linear systems. And by accumulating all the things, now we can find some kind of the solve this equation, finding the non-zero solution for this. So this is something about the linear algebra. And since we are running out of time, I'm going to get back to this point and see how exactly we can calculate this next time. So basically here the idea is that based on the fact that the cross product of these two should be the same, we can basically, given the set of the 3D2 and the 2D points, we can calculate this matrix P by solving the homogeneous linear system, which can be done by using the SVD or something, some different kind of things. So this is kind of the simplest idea in terms of that we can also find some kind of the camera matrix from some kind of given the correspondence between the 3D and the 2D points. So this is some kind of the basic things about the camera model. And based on this, what we are going to discuss next time is how we can do some kind of the 3D reconstruction from the multi-view images. So we're going to see the ideas for the multi-view to 3D reconstruction. And based on that, we're going to also see some limitations of that. And then we're going to move on to the neural rendering. Okay? And if you have any questions on this, please feel free to post the questions on the Slack. And I'm going to see you next Monday. Okay? Thank you.